Hello and a very warm welcome. Today's video is talking about side views and perspective, and it's been prompted by the comments that have been made on my videos about Traprain, or videos of an observation from Traprain Law in East Lothian in Scotland that proves the Earth cannot be flat. A number of people have objected to the way that I've presented the geometry of this particular observation. And I'd like to talk about that today. So just in case there are people watching who have not encountered my previous videos on the subject, I was located on a hill called Traprain Law. It's just to the east of Edinburgh and is a hill that's 221 meters at the summit. My camera was below the summit at 210 meters above sea level. I was looking towards the bridges that cross the River Forth and to the hills in the distance in the background. And the bridge tower, that's this particular bridge tower in the middle of the shot here, is also at 210 meters above sea level. This means that we can draw a line across the screen, and geometry tells us that if the Earth was flat, everything below that line must be less than 210 meters above sea level. Now, the other bridges are less than 210 meters above sea level, and the low hills in the foreground are also less than 210 meters above sea level. So there's no issue with those. But the hills in the background is a different story. This is Meikle Bin, which does extend above the line by a small amount, but is 570 meters above sea level, and it certainly appears that the vast bulk of that hill is below the line. Earl's Seat is 578 meters above sea level at its summit and appears to be all below the line. Dunbrack also all below the line at 540 meters above sea level. Now, Earl's Seat and Dunbrack might be level with the line, possibly even very slightly above the line, but they're very, very close, and the bulk of those hills is definitely below the line. There's no debate at all about Cairnach Hill, 413 meters at its summit and clearly well below the line. And Strawn End here at 511 meters above sea level also appears to be on or below the line at its summit. Since on a flat Earth everything below the line must be less than 210 meters above sea level, this observation proves that the Earth cannot be flat. It also happens to agree very well with the spherical Earth model that is the currently accepted scientific model of our Earth. Now, a number of flat earthers have objected to the use of this particular diagram in the analysis that I used partly in the analysis of the description of my observation in my early videos. So I'll just run through what the diagram is. So it has a vertical scale showing the elevation in meters, a horizontal scale showing distance in kilometers, and they're obviously different scales. The hill that I was on, Traprain Law, is indicated by the green triangle on the left, the bridge tower by the grey rectangle in the middle, and the hills in the background by the green triangle on the right. The red arrow indicates the line of sight from my camera to the tower and to the hills in the background, as it would be on a flat Earth. So I've used this diagram to show the relative locations, elevations of the hills and bridge tower. It is to scale, but the vertical scale and horizontal scales are different. It would not be possible to get them both on the same scale and fit on the screen. Now, flat earthers have objected to this on the basis that it takes no account of perspective. So I want to discuss this and see if they have a point. I'd like to use this particular example. Imagine a very long fence, and I mean very long, hundreds of meters, possibly even kilometers long, and two observers. First observer is close to the fence, and so their field of view, their width of view, means they can only see a small portion of the fence. I've actually made an observation like this in a school playground. Imagine this fence continuing many hundreds of meters to either side off screen. The portion that we can see is the portion straight in front of us. And these red lines show that the verticals of all the way along that particular section appear to be exactly the same height. And in fact, the ones straight in front of us might be very, very slightly taller than the ones next to it, but it's so small as to be unnoticeable. An observer much further away, who could see far more of the fence, all of the fence, would have a very different observation. So observer 1 sees the small section of fence shown at the top, but observer 2 would see something a little bit more like the bottom representation. The verticals of the fence, the vertical posts, reduce in size, or reduce in apparent size. Their angular size is smaller the further away they are from the observer. And that's what perspective does. Angular size reduction is something that happens, something that we observe when we look at things. So what is the correct way to present the side view from Traprain Law? Or of anything else? Is it correct to present it with the verticals all the same height, or is it correct to present it with the verticals getting smaller and smaller and smaller further to the side they are? Well, the answer is that both are correct, because both are showing something quite different. They're showing a different aspect of the same object. So the top one is showing how things actually are. The fence is the same height throughout its whole length. It may not look like that to an observer in one particular spot, but it is the same height throughout its whole length. The bottom one is showing how things appear, but only how they appear to one observer in one location. Observe that fence from any other location and you'll get a different view. You make a different observation. The representation, or the diagram, with the vertical height being the same throughout the whole length of the fence is most useful when you're building structures, such as a fence or some other structure that's on a flat level surface, a very long building, for example. Because that representation, that diagram, shows what the building or the fence will actually be like in reality when you've built it. Each of the vertical posts on the fence is the same height. And you want them to be the same height. And so you can use a diagram like this to show where you're going to put things. The side view at the bottom, the one that shows how the fence would appear once it's built to an observer standing at one particular position. It's not particularly useful if you're trying to build the fence. But if you were drawing a scene with a fence like that in it, or painting a scene with a fence like that in it, then this is how you would draw it. You would draw it, you make your picture as if there is an observer viewing that scene, and you would want to have the perspective in the drawing. But if you try to use that kind of diagram as a guide to constructing a fence, you would end up with a very, very different looking fence. Your fence would not match the fence from the diagram above, and it would not, when you looked at it, look like the diagram at the bottom. It would, the perspective effect would now be exaggerated because you would have taller verticals in the middle and shorter ones at the end. So both these kinds of representations have their place, and they're both trying to do different things. Now let's go back to my particular diagram. Let's consider the side view from Traprain Law that I use to represent reality. Now, please be aware that I'm not claiming this is how it would look to an observer viewing from the side at any specific location. It represents how the hills and the bridge tower would be located relative to one another if the Earth was flat. It is their relationship to each other, not how they would appear to an observer located at any particular position. If you want to think of it this way, imagine the red line as a very long and rigid pole. If the pole was laid on top of the bridge tower at 210 meters and extended back to the camera at 210 meters, and the other end extended to the Fintry Hills, it would contact those Fintry Hills at a point 210 meters above sea level. If you looked along that pole, you would see the top of the bridge tower lining up with a point 210 meters up the hills in the distance. You'd see the pole contacting the hills at 210 meters above sea level. So this is an accurate representation for what you would observe if you were on top of Traprain Law, looking along that red line towards the hills in the distance, and the Earth was flat. But on a flat Earth, it's simply impossible for a direct line of sight from the top of Traprain Law past the top of the bridge tower to line up with hilltops that are over 500 meters tall and between 90 and 100 kilometers further away. This is simply not possible on a flat Earth. Now, another criticism of my observation has been that I may have been an error in estimating or measuring the elevation of my camera above sea level. Well, that's a fair criticism. If the camera was a little bit higher than 210 meters, and the maximum height it could be is just over 221 meters, because that's the height at the top of Traprain Law, then line of sight would point downwards past the top of the bridge tower to a point on the hills in the distance a little bit below 210 meters. And that's indicated by the red arrow with the dashed line. If my camera was slightly lower than 210 meters, if I'd gone too far down Traprain Law before making the observation, then the camera would point upwards slightly past the bridge tower, and the bridge tower would line up with a point a little bit above 210 meters. Conveniently for me, the bridge tower is almost exactly halfway between Traprain Law and the hills in the distance. And so any error that I make with my camera will result in almost exactly the same amount of movement on the opposite side, on the hills on the opposite side. If the tower had been much closer to Traprain Law, then any error would be greatly exaggerated at the other end. But I hope you can see that a small error in my camera elevation measurement will result in very, very little error at the other end, and that cannot possibly account for the observation that we actually made. Continuing with the idea of an error in camera height, how much of an error would I have had to have made in order to get a 500-meter plus hill to appear level with the top of the tower? Well, it would need to be below sea level, as you can see from this line drawn on the screen. Now, the base of Traprain Law is 100 meters above sea level. So anyone claiming that I have simply gone to a lower elevation to take my picture or shoot my videos, and I've then pretended that I'm on top of Traprain Law, firstly hasn't looked at the videos, which clearly show I'm at the top of Traprain Law. But it's impossible for me to have found a place where I could have faked this picture by taking the camera to a lower elevation. I would have had to have dug a 100-meter deep hole in the ground at the foot of Traprain Law, got to the bottom of it, and somehow still been able to see the bridge towers and the hills in the distance. It's just absurd to suggest that my camera height measurement is so errant that it accounts for the observation. Please also note that tilting the camera makes no difference to the line of sight and therefore the parallax or the appearance of the hills and the bridge tower in the frame, in the field of view. I've shown some videos where the bridge tower moves around in the frame all over the place, sometimes at the top, sometimes at the bottom, sometimes at the left, sometimes at the right. It makes no difference at all to the relationship between the top of the bridge tower and the hills in the distance. The hills in the distance are always at the same height as the tower or lower in the case of Cairnach Hill. And that does not change when the camera is tilted. So tilting the camera makes no difference. There is still a direct line of sight from the sensor on the camera through the lens of the camera to the bridge tower and to the hills in the distance. Just for fun, and not because it's remotely valid, I decided to calculate the angular sizes of Traprain Law, the bridge tower, and Cairnach Hill. From the point of view of a person standing perpendicular to the screen here, at level with the bridge tower, but 46.5 kilometers from the bridge tower, so that you would have a sufficiently wide field of view to get all three objects into the same shot, potentially. This is now drawn to scale for the angular sizes from that particular location. So this is taking perspective into account. This is drawing a side view with perspective taken into account. This is a completely false representation of reality, utterly false. But it shows that even if you do this mathematical fudging that flat earthers seem to think might be valid, a camera located at the top of Traprain Law, looking over the bridge tower to the hills in the background, should still see the hills in the background appearing above the top of the bridge tower. So not only is the observation I've made impossible on a truly correct mathematical geometrical drawn flat plane, but it's also impossible on the fantasy world that flat earthers occupy. Thank you for watching.